ME350 example problem for lump capacitance method for a coin heating on a hot plate. A metal coin with properties as specified, a thickness of 2 millimeters and a top surface area of 5 square centimeters, is at equilibrium in a room at a temperature of 20 degrees Celsius. Initially, at time zero, it is placed on a hot plate that delivers a constant surface heat flux of 10 kilowatts per meter squared to the bottom of the coin. For a convection heat transfer coefficient of 500 watts per meter squared Kelvin for the top, find for part A the temperature at steady state, for part B the change in energy storage for the coin while reaching steady state, for part C the temperature of the coin after a time of 10 seconds, and for part D the change in energy storage for the coin during this time period. Our first assumption for this problem is that the temperature within the coin is uniform at each instant in time. Use of this assumption is called the lumped capacitance method, and we will calculate the Biot number to ensure that this is a valid assumption. Our second assumption is constant properties, which is reasonable as long as the properties have less than a 10% variation over the range of conditions. Our third assumption is that there is negligible internal heat generation within the coin. Our fourth assumption for this problem is negligible radiation for the exterior boundary. This is a reasonable assumption for an opaque coin and for moderate temperatures combined with significant convection at the exterior boundary. Our fifth assumption is negligible conduction from the sides of the coin because it is thin. We could include the sides, but this makes the algebra a little simpler, and we get the same answer to 3 decimal places. Our sixth assumption is that the coin has uniform thickness. For part A, to find the steady state temperature, we apply an energy balance as a rate equation to a control volume that contains the entire coin. Once we reach steady state, the rate of change of energy storage term is 0. By assumption 3, the energy generation term is also 0. Thus, this equation reduces to a balance between the thermal energy added by the hot plate with the thermal energy out by convection to the fluid at each instant. Substituting in Newton's law of cooling for convection, we solve for a steady state temperature of 40 degrees Celsius. For part B, to find the change in energy storage while reaching steady state, we recall that it is equal to the change in internal energy for sensible energy changes only. Then, we use the definition of specific heat to calculate the change in internal energy for our known mass and known temperature change for the coin. Note that the temperature change is from our initial condition, where the coin is in equilibrium with the surrounding fluid, to our final steady state condition, which is the temperature calculated for part A. Substituting in values, we get an addition of 50 joules of energy to the coin. Before continuing, we rewrite the energy storage change equation by substituting in the equation for steady state temperature from part A. We will use this equation later to verify our results for part D. For part C, before we begin our transient analysis, the first task is to check the magnitude of the Biot number, which is a dimensionless parameter that compares the rate of convection at the surface of a body to the rate of conduction within the body. A Biot number less than 0.1 indicates that the body conducts heat well enough to be approximately at a uniform temperature throughout. Note that the characteristic length used for this calculation compares total volume of the body to the surface area for convection. For our coin with convection only on one side, we get that this is equal to the coin thickness. Plugging in values, we get a Biot number of 0.01, which is an order of magnitude below 0.1. Thus, using the lumped capacitance method has been shown to be valid. Before continuing, just for fun, we solve for the largest thickness for which the lumped capacitance method would be valid. For these conditions, our coin can be up to 2 centimeters thick. We now begin our analysis by applying conservation of energy as a rate equation to a control volume that contains the coin, which is the same as for part A. By assumption 3, the energy generation term is still 0. However, we are now solving for temperature as a function of time and must keep the energy storage term. Thus, this equation reduces to a balance between the thermal energy added by the hot plate minus the thermal energy out by convection to the fluid and the energy stored in the coin at each instant. Substituting in Newton's law of cooling for convection, we get an ordinary differential equation because the temperature only depends on time. Next, we substitute in theta, tau, b, and theta prime, which are defined as shown. Separating variables, we integrate this equation from our initial time to the final time. Finally, we solve for an equation for the temperature as a function of time. We see that the final temperature will asymptote exponentially towards a constant value as time goes to infinity. Substituting in values, we first calculate a value for tau of 10 seconds. Note, this quantity represents a time constant for our process, which we will consider further on the final slide. Then we calculate a value for B of 2 Kelvin per second. Finally, we calculate the temperature after 10 seconds to be 32.6 degrees Celsius, which is still pretty far away from our steady state temperature of 40 degrees Celsius. Before continuing, we verify that as time goes to infinity, we get the same steady state temperature as for part A as expected. For part D, to solve for the change in energy storage as a function of time, we again begin by applying conservation of energy as a rate equation to a control volume that contains the coin. By assumption 3, the energy generation term is still 0. This time, however, we keep the energy storage term as it is written and only substitute in for the thermal energy added by the hot plate minus the thermal energy out by convection to the fluid at each instant. Substituting in Newton's law of cooling for convection, we get an equation for the rate of change in energy storage as a function of time. Next, to get the change in energy storage over a period of time, we integrate this rate equation from the initial time to the final time. The result of our integration shows that the change in energy storage will also asymptote exponentially towards a constant value as time goes to infinity. Substituting in values, we get a change in energy storage of 31.6 joules, which once again is still pretty far away from our steady state energy change of 50 joules. Before continuing, we verify that as time goes to infinity, we get the same steady state energy change as for part B as expected. To consider these results further, I have used our earlier results to plot the temperature and change in energy storage of the coin as a function of time. Looking at the figure, we see that both the coin temperature and change in energy storage asymptote exponentially towards their steady state values with time. Again, note that tau, which has units of time, represents a time constant for the process. After one time constant, which corresponds to the conditions specified for this example, the change in both temperature and energy storage is 63.2%.